Okay, let's unpack this. For a while now, we've been living in this really clean, perfectly behaved world of the ideal gas law.
It's a beautiful model, PV and RT day. Simple, elegant.
So elegant. It's like the first draft of chemistry, but it's really built on a foundation of two, I guess, kind of naive assumptions about how matter actually works.
I think bold is the word. It assumes particles are just mathematical points and that they never interact.
And that works great, for gases at really low pressures or hot
Right.
temperatures. But the second you want to model reality, where things can actually condense or freeze.
The model just completely falls apart. It has no mechanism for phase changes.
So that's our mission for this deep dive. We're going into the messy, fascinating reality of real substances. We're going to look at why that ideal model fails and what we replace it with.
Precisely. We're going to build up the physics from the ground, starting with the corrections to the ideal gas law. We'll map out phase transitions, and then we'll get into some really strange territory like non-equilibrium states and the famous weirdness of water.
So we have this great stack of sources here laying it all out. To start, let's go back to those two failed assumptions. What exactly did we ignore about atoms that the ideal model just couldn't handle?
Well, we ignored pretty much everything that makes them real. We ignored that they have volume, and we ignored that they're sticky. They attract each other. And fixing those two things is the entire genius of the Dutch physicist Johannes van der Waals.
Right. This is his famous equation of state for real gases.
It is. And what's so incredible is how elegantly he corrects for those two simple fundamental facts.
So let's start with the first one, the volume issue. The ideal gas law pretends particles take up zero space, which is, obviously not true.
That is flaw number one, finite volume. Sources sometimes call it eigenvolume and the self-volume. Atoms have electron clouds. They have a physical size. They're like tiny, hard billiard balls, not mathematical points.
And if you start squeezing those billiard balls into a smaller and smaller box, their own volume starts to matter a whole lot.
It becomes a significant fraction of the container's volume. Exactly. So the actual space available for any one particle to move around in isn't the total volume of the container, V. It's V minus the volume that all the other atoms are already taking up.
So the V in the ideal gas law is misleading. It should be the free volume, the empty space.
That's the correction. Van der Waals introduced a term, B, which we call the excluded volume or covolumen. It's basically the volume per mole that the atoms themselves occupy.
And you just subtract it.
You just subtract it. So the volume term in the equation becomes VMB, where V is the molar volume, and that B term sets a hard floor. You physically cannot compress a substance beyond that volume because the atoms themselves are in the way.
Okay, that part is pretty intuitive. It's just geometry. But flaw number two, the intermolecular forces.
Mm-hmm.
That's where the really complex, interesting behavior starts to emerge, isn't it?
This is where things get sticky, literally.
Right. The ideal model assumes particles just bounce off each other perfectly, no attraction, no nothing.
But in reality, they all attract each other through these short-range forces we call van der Waals forces. Now, they're weak over long distances. They fall off really fast, proportional to 1 over the distance to the 6th power. But they are always there.
Can you kind of paint a picture of how that attraction works on a microscopic level?
Sure. Imagine two atoms approaching each other. If you plot their potential energy, you get what we call a potential well. At a distance, they feel a slight attractive tug. They're sort of falling into this energy well.
And that's the source of this internal pressure the sources mentioned, the Binnendruck.
That's it exactly. That's the cohesive force. As they get closer, they hit a sweet spot, a minimum in the energy. If the random thermal energy of the system isn't enough to overcome the depth of that well, they'll stick together. That's condensation.
And if they get too close?
If they try to get even closer, their electron clouds start to overlap, and you get this massive repulsion. The energy curve shoots up almost vertically. And that steep wall of repulsion, that's the hardcore size we already accounted for with the Bib term.
So you've got this sweet spot of attraction and then a hard wall of repulsion. How does that stickiness affect the pressure we actually measure on the walls of the container?
This is the second brilliant insight from van der Waals. Picture a particle heading for the container wall. All the other particles in the bulk of the gas are behind it, pulling it back.
Oh, right. They're all tugging on it with that attractive force.
It's like it has a tiny invisible bungee cord pulling it back toward the center, so when it finally hits the wall, it hits with less force than it would have otherwise.
Which means the pressure we measure, the P, is always a bit lower than the true internal thermodynamic pressure.
Always. So to fix the equation, we have to compensate. We have to add a correction term to the measured pressure P to account for this missing force. And that term is AVM2.
Okay, hold on. The Vm squared dependence, that's the part that always trips people up. Why density squared? Why not just density?
It's a really neat statistical argument. Think about it in two parts. First, you have the strength of the backward pull on any single molecule that's about to hit the wall. That pull is proportional to the density of the molecules behind it, right? More pullers, more pull.
Okay, that makes sense. So proportional to density.
Right. But second, the number of molecules hitting the wall per second is also proportional to the density. More attackers, more hits.
Ah, I see. So you're multiplying the effect.
You're multiplying the two effects. The reduction in force for each collision is proportional to density, and the number of collisions is also proportional to density. So the total effect on the pressure scales with density times density, which is density squared. And since density is proportional to 1 over the molar volume, the term becomes AVM to 2.
That's a great explanation. So A is just a constant for how sticky that particular gas is.
Exactly. So you put it all together, you take the ideal gas law, you replace P with map P plus AVM day.
Yeah, and you replace V with Vm in.
And you get the Van der Waals equation of state, BP plus AVM2 VMB equals RT2. And what's just so profound is that by accounting for two simple ideas, stickiness and size, this one equation unlocks the ability to describe both the gas and the liquid phase. It predicts condensation.
And we can see that prediction come to life when we plot the isotherms, the curves of pressure versus volume at a constant temperature.
Right. At very high temperatures, the curves look almost exactly like the ideal gas hyperbola. The thermal energy is just too high for the stickiness to matter.
But then you cool it down.
As you cool it down, as the thermal energy gets closer to the depth of that potential, well, the isotherms start to bend.
Yeah.
They develop this characteristic S shape, a belly with a peak and a trough.
And that belly is where the phase transition should be happening, but the math itself describes something physically impossible, right?
It describes a region of absolute thermodynamic instability. If you follow that curve, it suggests there's a point where compressing the gas, shrinking its volume, would actually cause the pressure to decrease.
Which can't happen.
It's absurd. You can't squeeze something and have it push back less. That instability is the equation's way of screaming at us that the system can't stay in a single homogeneous phase anymore. It has to separate. It has to condense.
So in the real world, we don't follow that wiggly S-curve. The system takes a shortcut. It draws a flat horizontal line.
That's the Maxwell construction, the Maxwell gerade. That horizontal line is reality. It represents the coexistence of the liquid and vapor phases. As you compress it, the pressure stays perfectly constant at what we call the saturated vapor pressure.
You're just converting more and more gas into liquid at that constant pressure.
Exactly. You're just moving along that line, changing the ratio of liquid to gas until everything is liquid. And then the pressure shoots up again because liquids are nearly incompressible. That transition from the theoretical S-curve to the real flat line is just a beautiful moment where math meets physical reality.
Okay, so now that we have the microscopic mechanism for condensation, let's zoom out. Let's look at the big map of all the phases. The pressure-temperature diagram, the PT diagram.
This is our master guide to stability. For any given pressure and temperature, this diagram tells you which phase, solid, liquid, or gas, is the most stable one.
And the lines on the map are the boundaries. That's where two phases can coexist in equilibrium.
Right. You have the sublimation curve between solid and gas, the melting curve between solid and liquid, and the one we've just been discussing, the vapor pressure curve between liquid and gas.
And there's one really special spot on this map where all three of those lines meet.
The triple point. It's the one unique combination of pressure and temperature where solid, liquid, and gas can all exist at the same time in perfect dynamic equilibrium.
And it's incredibly precise, isn't it? That's why it's used as a scientific standard.
It's the ultimate reference point. For water, it's at exactly 0.01 degrees Celsius and a tiny pressure of about 6 millibars. Because that point is fixed by the fundamental laws of physics for water, it's used to define the Kelvin temperature scale. It's a non-negotiable point set by nature.
Okay, so if the tricky point is where the lines meet, let's follow the vapor pressure curve upwards. And here's where it gets really interesting. The line just stops.
It terminates at the critical point. This is another one of these absolute thermodynamic limits. It's defined by a critical temperature and a critical pressure.
And above that temperature, what happens?
Above that critical temperature, The random thermal energy of the molecules is just so high that it completely overwhelms the attractive forces. That potential, what we talked about, the stickiness becomes irrelevant,
So you can't force it to condense anymore.
no matter how hard you squeeze it. Above the critical temperature, you cannot get a distinct phase transition. You can't make a liquid with a sharp surface, a meniscus. The distinction between liquid and gas has vanished.
So what do you have then? If you take a gas and you compress it above its critical temperature, what is it?
You have a supercritical fluid. It's this strange hybrid state of matter. It's dense like a liquid, but it expands to fill its container like a gas. It flows with very little viscosity, almost like a gas.
Is this just a lab curiosity, or does it have real-world applications?
Oh, it's hugely important industrially. Supercritical carbon dioxide, for example, is a fantastic solvent. Its critical point is only about 31 degrees Celsius, so it's easy to work with.
And what do you use it for?
Decaffeinating coffee is the classic example. You run supercritical CO2 through the coffee beans. It's dense enough to dissolve the caffeine, but it flows through everything like a gas, and it does it without high temperatures that would destroy the flavor compounds. Then you just release the pressure, the CO2 turns back into a gas and leaves the caffeine behind.
That's incredible.
Right.
So you can go from something that's clearly a gas to something that is clearly a liquid without ever crossing a phase boundary, without ever seeing a bubble or a drop form.
You can just go around the critical point.
Yeah.
You heat the gas up, compress it, then cool it down, and you end up with a liquid. The density just increases continuously. It shows that, in a way, liquid and gas aren't fundamentally different states. They're just different ends of a density spectrum.
Which brings us right back to that vapor pressure curve. We know it exists, but we also know it's incredibly steep. A small change in temperature causes a huge jump in vapor pressure. Why is that relationship so explosive, so nonlinear?
It takes us right back to the microscopic world again. This time, not to van der Waals forces directly, but to how energy is distributed among the molecules. It's all about the Boltzmann distribution.
Okay, remind us of the basics here.
Well, a liquid is a bound system, right? The molecules are all stuck in that potential well. To escape, a molecule needs a certain amount of energy, the binding energy, WW. But not all molecules have the same energy.
Right, there's a distribution. Some are slow, most are average, and a few are really, really fast.
And that's the key. There's always this small fraction of high-energy particles in what we call the hot tail of the Boltzmann distribution. Only those particles, the ones whose kinetic energy happens to be greater than the binding energy W, have enough oomph to break free and escape into the vapor phase.
They're the statistical escapees.
They are. And because the Boltzmann distribution is an exponential function, the number of particles in that hot tail is proportional to a WKB-TT.
Ah, and there's the exponential dependence. The t is in the denominator of the exponent.
That is the absolute key. A small increase in temperature, T, causes a massive, disproportionate increase in the number of particles that have enough energy to escape. The size of that hot tail just explodes upwards.
More escapees means more evaporation, which means a much higher vapor pressure.
A massively higher vapor pressure. It's why leaving a puddle of water out on a 25-degree day versus a 30-degree day makes such a huge difference in how fast it disappears.
So when you put this liquid in a sealed container, you get this dynamic equilibrium, the saturated vapor pressure.
Right. You reach a point where the rate of particles escaping the liquid is exactly balanced by the rate of particles from the vapor crashing back into it and getting stuck again. And crucially, that equilibrium pressure depends only on the temperature, not the size of the container, as long as you still have some liquid left.
This explains so many everyday things, like boiling.
Boiling is just the point where the saturated vapor pressure of the liquid becomes equal to the external pressure of the atmosphere around it. For water at sea level, its vapor pressure has to reach 1 bar, or 100,000 pascals.
And that happens to occur at 100 degrees Celsius.
Precisely. If you're on top of the mountain, the atmospheric pressure is lower. So the water's vapor pressure doesn't have to climb as high to match it. It will boil at, say, 90 degrees.
Which is why it's hard to cook pasta up there. The water's not as hot.
Exactly. And the same principle is behind evaporative cooling, the Verdunstungskälte.
Right, because only the fastest, hottest particles escape.
Only the hot tail leaves, which means the average kinetic energy of the molecules left behind goes down. And a lower average kinetic energy is, by definition, a lower temperature. That's the physics of sweating. Your body is using the massive amount of energy needed to vaporize water to dump excess heat.
And this all ties into air humidity and the dew point.
It's the same curve at work. Relative humidity is just a percentage. It's the ratio of how much water vapor is actually in the air compared to the maximum amount the air could hold at that temperature, which is the saturation vapor pressure.
And warm air can hold a lot more water vapor than cold air because its saturation pressure is so much higher on that exponential curve.
A lot more. So if you take warm, humid air and you cool it down, its capacity to hold water vapor drops steeply. Eventually, you'll hit a temperature where the actual amount of water in the air is the maximum amount it can hold. The relative humidity hits 100%.
That's the dew point.
That's the dew point. Cool it down any further and the water has nowhere to go. It has to condense out as liquid. That's the dew on the grass in the morning, or the fog you see, or the condensation on a cold glass. It's a forced phase transition.
Okay, it's amazing that the microscopic Boltzmann statistics explain so much. But that's a qualitative explanation. How do we get quantitative? How do we calculate the exact steepness, the PDTT, of that vapor pressure curve?
For that, we need one of the most powerful tools in thermodynamics, the Clausius-Clapeyron equation. It's a beautiful derivation because it connects thermal energy heat directly to mechanical properties like pressure and volume.
And it doesn't use statistics. It uses the laws of thermodynamics, right?
Yeah.
With a Carnot cycle.
Exactly. The conceptual setup is to imagine an infinitesimally small, perfectly efficient Carnot engine that runs in a cycle right across the phase boundary, say, from liquid to gas and back.
So walk me through this tiny engine. What are the steps?
Okay, so you start with the liquid. Step 1, you let it expand and vaporize at a constant temperature T, and to do that, it has to absorb heat. That's the latent heat of vaporization, lambda.
Right. The energy needed to break the bonds.
Step 2, you let it expand a tiny bit more, adiabatically, so it cools down by an infinitesimal amount, ddt. Step 3, you compress it back into a liquid at this new lower temperature, T minus dt. And step 4, you compress it adiabatically to get back to where you started.
And because it's a cycle, the area inside that little loop on a PV diagram is the network done by the engine.
Precisely. And for a tiny little rectangle like this, the work done is just the change in volume, delta V, that's the volume of the gas, minus the volume of the liquid times the change in pressure, dP.
So work equals delta V times dP.
Now, here comes the magic. We know the efficiency of any Carnot engine is just the temperature difference divided by the high temperature. So efficiency is dT over T. But we also know efficiency is the work you get out divided by the heat you put in.
Which is the work, W, divided by the latent heat, lambda.
So we just set them equal. dT over T equals W over lambda, which is delta V times dP, all over lambda. You rearrange that to solve for the steepness of the curve, dt pdtt, and you get it. The Clausius-Clapeyron equation.
Man, but TPD delta lambda.
And that is just incredibly powerful. It tells you that the slope of the phase boundary depends on the latent heat thermal property and the change in volume mechanical property. It connects the two worlds.
And this is where we get that big aha moment where this classical thermodynamic result connects back to the statistical Boltzmann idea.
This is it. We can simplify this equation for the liquid to vapor transition. First, the volume of the liquid is tiny compared to the volume of the vapor, by a factor of 1,000, usually. So we can pretty much ignore it.
So delta V is just the volume of the vapor.
Approximately. And then for the vapor, we can use the ideal gas law as a pretty good approximation. So we substitute V equals RT over P.
And when you plug that into the Clausius-Clapeyron equation,
you get a differential equation that you can actually solve. It basically says that BBTT is proportional to DTT to 2. And when you integrate that,
you find that the natural log of pressure is proportional to -1 over T.
Which means that pressure itself must be proportional to e to the power of negative latent heat over RTPT, prop derived R.
So the abstract Carnot cycle derivation gives us the exact same exponential form that we predicted from the microscopic Boltzmann statistics.
The two approaches converge perfectly. It's one of the most satisfying results in physics. It proves that both ways of looking at the world, the macroscopic thermodynamic and the microscopic statistical, are consistent and correct.
And this has real practical use in the lab, right?
Oh, absolutely. Because the relationship between the log of pressure and 1 over temperature is a straight line, you can find the latent heat of a substance without ever measuring heat flow. You just measure its pressure at a few different temperatures, plot log P versus 1 over T, and the slope of that line gives you the latent heat. It's an amazing shortcut.
That's brilliant. But the source material adds a little nuance here. That latent heat, lambda, isn't actually a constant.
That's a very important point. Lambda is the energy you need to break the cohesive bonds. As you go to higher temperatures, the molecules are already jiggling around more violently. The substance is already less bound, so it takes less additional energy to make them vaporize. Lambda decreases as temperature increases.
And it goes to zero at the critical point.
Exactly. At the critical point, the distinction between liquid and gas is gone. There are no more cohesive bonds to break to make the transition, so the energy required for the transition, the latent heat, becomes zero. The phase transition itself just fades out of existence.
Okay, so we've mapped out the stable regions. But let's go to the edges now, to the unstable non-equilibrium states. This is when we sort of trick the system into staying on that theoretical van der Waals curve for a moment.
These are these metastable states. They're thermodynamically unstable and shouldn't exist, but you can achieve them under very, very clean and careful conditions.
The first one is supersaturation, or Übersättigung. This is where you have a vapor that's at a higher pressure than its saturation point. It should have condensed, but it hasn't.
It's holding more vapor than it should be able to. The only reason it can do that is a lack of what we call a nucleation seed, a chyme. For condensation to start, the first few molecules need something to grab onto, a tiny dust particle, an ion, some impurity.
And if the air is perfectly clean, there's nothing for the first drop to form on.
Right. So the vapor can remain in this precarious, supersaturated state. But if you introduce a single dust particle or create an ion, you can trigger a sudden, rapid condensation event.
And the opposite of that is superheating, Siederversuch, a liquid that's hotter than its boiling point, but isn't boiling.
This one can be really dangerous in the lab. Boiling, just like condensation, needs nucleation sites. Tiny scratches in the glass, dissolved air pockets, something for the first bubble of steam to form on.
And if you're heating, very pure water in a very smooth, clean flask.
There might be no sites. So the water gets hotter and hotter, way past 100 degrees, holding all this thermal energy with no way to release it as steam. It's trapped.
Until you disturb it, you tap the glass or drop something in.
And you provide that one nucleation site, and the whole thing can vaporize instantly and explosively. It's why in a chemistry lab, you always add boiling stones, little porous chips that provide a steady stream of bubbles to ensure a nice, smooth boil.
What's so cool is that physicists took these dangerous instabilities and turned them into tools for discovery, for seeing the unseeable.
They turned them into the great particle detectors of the 20th century. First, the cloud chamber.
The Nebelkammer, that uses supersaturation, right?
It does. You create a chamber filled with supersaturated alcohol or water vapor. It's primed, ready to condense. Then, a high-energy particle from a cosmic ray or a radioactive source zips through.
And as it travels, it rips electrons off the atoms it passes. It ionizes them.
And those ions become the perfect nucleation seeds. The supersaturated vapor instantly condenses into a line of tiny fog droplets all along the particle's path. You literally see the track of a subatomic particle.
And then came the bubble chamber, which uses the opposite principle, superheating.
The bubble chamber starts with a large volume of a superheated liquid, often liquid hydrogen, held just on the brink of boiling. When a charged particle flies through, it deposits a tiny amount of energy along its path, creating a little trail of micro-hotspots.
Which act as the nucleation sites for boiling.
Exactly. You get explosive bubble formation all along the particle's track, so instead of a line of fog, you see a line of tiny expanding bubbles.
And for both chambers, if you put them in a magnetic field, the paths of charged particles will curve.
And by measuring the radius of that curve, you can calculate the particle's momentum. It's just an astonishingly clever way to use basic phase transition physics to do fundamental particle research.
Let's come back to water for this last part. We've used it as an example a lot, but it has this one really profound secret that breaks all the rules. Its density anomaly.
This is where we have to go back to the Clausius-Clapeyron equation one last time, but now we apply it to the melting curve, the boundary between solid and liquid.
Okay, so the equation is the same. Delta T, delta d day. But this time, delta V is the volume of the liquid minus the volume of the solid.
Right, and for almost every substance we know, wax, metal, CO2, when it melts, it expands. The liquid takes up more space than the solid.
So for a normal substance, delta V is positive, which means delta dt is positive. If you increase the pressure, you have to increase the temperature to get it to melt. The melting point goes up.
That is the normal expected behavior. But water. Water is the great exception. Normal ice, the kind that floats, ice I, is less dense than liquid water. Its hexagonal crystal structure, because of hydrogen bonding, is very open and takes up a lot of space.
So when ice melts, it actually shrinks.
It shrinks. The volume of the liquid is less than the volume of the solid, which means delta V is negative.
And if delta V is negative, the whole right side of the equation is negative. dT dt is negative.
The melting curve for water slopes to the left on the phase diagram. This is the famous density anomaly in action. If you increase the pressure on ice, you lower its melting point.
That's so counterintuitive.
It is. The sources show that if you put ice under about 2,000 bars of pressure, it will stay liquid all the way down to -20 Celsius. The pressure is actually helping it melt because the liquid state takes up less volume, which the system prefers under high compression.
And this is partly the reason given for why ice skates work. The immense pressure under that thin blade lowers the melting point of the ice, creating a tiny layer of water to glide on.
That's the classic application, yes. It's a direct consequence of that negative slope.
But the sources say this weirdness only applies to normal, everyday ice. Icing. If you keep cranking up the pressure, things change again.
They do. Above about 2,000 bars, the open hexagonal structure of ice, I can't take the strain anymore, it collapses. The pressure forces the water molecules into new, much denser crystal arrangements. We call them ice 2, ice 3, ice V, ice 6, and so on.
These are high-pressure ice polymorphs.
Right.
And they are denser than liquid water.
Much denser. If you had a chunk of ice 6, it would sink like a stone in liquid water.
Which means their melting behavior must go back to normal.
Exactly. For these dense ices, when they melt, the volume change, delta V, becomes positive again. So their melting curves slope back to the right, just like a normal substance. dTT is positive. To melt ice 6, you need both high pressure and high temperature.
And these exotic ices aren't just a lab curiosity. They could exist elsewhere in the solar system.
They almost certainly do. Planetary scientists believe the deep interiors of icy moons like Europa and Ganymede, and maybe even the cores of planets like Uranus and Neptune, are made of these high-pressure ice polymorphs. Understanding their phase diagrams is critical to modeling what's going on deep inside those worlds.
This has been an incredible journey. We started with 2 simple corrections to an old law and ended up inside the moons of Jupiter. So what does this all mean? What's the big takeaway for you, the listener?
I think it means that the real world is just infinitely richer and weirder than our simple models would suggest. We saw that the entire phenomenon of phase change boils down to 2 simple ideas. Atoms have size, and atoms are sticky. That's the van der Waals correction.
And we saw that the wild exponential rise of vapor pressure comes directly from the statistics of energy distribution, the Boltzmann hot tail, a concept we could then prove rigorously with the beautiful classical thermodynamics of the Carnot cycle and Closey-Cleveron.
And we learned that water, the substance we think we know best, is a thermodynamic rebel. Its unique density anomaly flips its phase diagram upside down, leading to all sorts of strange behaviors and exotic forms of ice that might shape entire other worlds.
We also saw that even the unstable parts of these theories, the parts that shouldn't exist, can be harnessed. We can use supersaturation and superheating to build detectors that let us literally see the paths of the fundamental particles that make up our universe. The ideal model is the starting point, but the messy reality is where all the interesting physics happens.
Which leads perfectly to a final provocative thought for you to take away. We've talked about these high-pressure ices, like ice Vigai, that are denser than liquid water. Now imagine a place deep inside an icy moon where you could have a subterranean ocean of liquid water trapped not on rock but squeezed between a layer of normal floating ice above and a layer of sinking high-pressure ice below. How would life or geology or chemistry even work in an environment like that, where liquid water is trapped between 2 different solid forms of itself? That's something profound to mull over until our next deep dive.